Hey everybody. Getting close to the end here. We're distinguishing between nuclear reactions and chemical reactions. We're defining what an isotope is and interpreting isotopic notation. We're going to talk about radioactivity and strong force, write nuclear equations, and discuss damage that radiation can do to cells. Alright, I recommend chapter 25. It's actually pretty interesting and you can learn a lot. So read 25 and 21 and 2 to get an automatic 10 out of 10. Read those sections and do the vocab definitions in the guide for reading. Okay, 10 points, easy way. Alright, so you might wonder what an isotope is, but you should know. Get out a periodic table for a symbol of an element. The mass number is the number of protons and neutrons, and then the atomic number is the number of protons. So look, it's sulfur 34. That means it's an isotope of sulfur with a mass number 34 and atomic number of 16. Where did I get that? Periodic table. Okay, so this means that this sulfur isotope has 16 protons and 18 neutrons. Right? If it's neutral, it also has 16 electrons. So make sure that you can still write these, even though it was a long time ago when we first learned them. Okay, this is the atomic number. This is the average atomic mass. But when we do mass number, it's a certain isotope of the element. So why do we need to know about isotopes? Well, when we talk about nuclear reactions, we know they're different from chemical reactions. Chemical reactions have the same atoms all the time, at all times. So if you have a nitrogen on the left-hand side of the arrow, you better have a nitrogen on the right, or else it's not a chemical reaction. Nuclear reactions change the identity of the atoms because the nucleus changes, so you get different atoms. So let's decide what this is. Well, we have polonium-210 reacts to form helium-4 and lead-206. So we're going to find out what this really is in a little bit. But notice none of the atoms are the same from the left to the right. But what is the same is if you look at that 210 and you add up those, you get 210. If you look at the bottom, you get 84. You add up those, you get 84. So there is some balancing going on, but the atoms don't stay the same. Okay, check out the next one. Lead turns into this thing, whatever it is. We'll learn, beta particle. And this isotope of bismuth. So this is nuclear. This is nuclear. And let's check out this one. So we have nitrogen plus 3 hydrogen molecules equals 2 ammonia molecules. Wait a second, this is chemical. How do I know? Because look, there's your nitrogen, 2 of them. Here's your 6 H's, 6 H's. This is a chemical reaction because the atoms don't change identity, they just bond differently. Okay, so what does radioactive mean? Radioactive means that the atom or isotope of atom gives off radioactivity. Okay, and when things are radioactive, it's because they're unstable. So this band right here is called the band of stability, and every dot on the band represents a stable nucleus that is not radioactive. But if there's a nucleus that is not stable, it gives off radiation to become stable. Okay, so there's all kinds of radiation. We're going to talk about nuclear radiation, and these kinds of radiations. Radon, it gives off nuclear radiation. There's different kinds of electromagnetic radiation. But we're going to find out that these atoms on this band, these dots represent stable nuclei, and they don't give off radiation. But any nuclei that aren't on the band are unstable and do give off radiation. Okay, what kinds of radiation would an unstable nucleus give off? Well, here we go with alpha decay is one of them. Alpha decay. So this Greek letter alpha. The symbol for alpha decay is 42He or 42 alpha. And it means it has 2 protons, and then this top number is 4 because it has 2 protons and 2 neutrons. It's heavy for a radioactive particle because it has a mass of 4. It's also positive. It's positive 2 because it has 2 protons. It doesn't have any electrons. So it's not a helium atom. It's a helium nucleus because it doesn't have the electrons to make it a helium atom. Okay, and because it's a heavy type of radioactive particle, it doesn't have much penetrating power. It means that skin can block it, blocked by skin. It can also be blocked by paper, clothing. So if alpha radiation is hitting you right now, it's not getting into your body because it's blocked by skin and paper and clothing. Okay, it does cause damage to cells though. Well, if it does get into your body and you breathe it in, it can get in your cells. And when it hits your cells, it can cause damage to cells, because even though it's kind of a it's a pretty big particle, it gets blocked by skin and paper. When it hits a cell, it can cause some damage. Okay, so here's a nuclear reaction with an alpha decay. Look, it's an alpha particle, looks the same as that. So this is an alpha decay. And hey, what element is this? Well, we don't know, but we can look it up. This is lawrencium, and it's element 103. And then when you look at this is a alpha particle, and so then this 103 has to equal 103 on this side, so that means this has to be a 101. So now I know what element it is. It's mendelevium, because mendelevium's element 101. Now, how do I figure out the mass number? 256 on the left side of the arrow is 4 plus that is 252. It has to be 252, so that these two add up to 256. So this is mendelevium 252. All right, so if I tell you that holmium goes through goes through alpha decay, and right away you'd write a 4,2 He, because you know that this gives off alpha radiation to become stable, and then this bottom number has to make the total 67. So I'm going to put a 65 because that's 67, and I'm going to put a 147 for this to equal 151. Now, how do I know what symbol to put? Well, I look up on the periodic table and I find Tb terbium as element 65. Okay, so how do you write an alpha decay reaction? Well, we show the alpha particle on the product side of the arrow, and then the new nucleus, which you use the periodic table to find. All right. So what other kinds of radiation are there? Well, there's beta decay. This is beta decay, and this is a Greek letter beta. So you can write a 0, -1 E, or a 0, -1 Greek letter beta for beta decay. So what is different about this than alpha? Well, this is a -1, so it's a -1 charge. Okay. And this means, hey, it has a mass number of 0. So how can a particle have a mass of 0? Well, it actually doesn't have a mass of 0, but it's very light compared to a proton or a neutron. So it takes about 2,000 of these particles to have the same mass as a proton. So it's light overall. It's basically a high-speed electron coming out of a nucleus in order to make the nucleus more stable. So because it's a lighter particle, it can move faster, it can penetrate more than alpha particles can. So you might need foil or metal to block it. Right? And so let's write a beta decay equation. So this is americium. Hey, how come there's a Z there? Oh, because you can look it up. This is all big. And so I am finding the 95 on the periodic table for americium. So I know this is a beta particle. So anytime you know it's beta decay, you can automatically write that. And it also produces this particle, which is not really AZX. This is -1, this is 95. So this has to be 96, because when you add them, you should get 95. So now I know what element it is. It's CM. Okay, so CM 96, and then the top number, this is 0, so this has to be 247. So this is not what it is. This is what it is, because when you add these up, you get 95 on both sides and 247 on both sides. Oh, look, it's gold. Hey, you, give me that gold chain back. Okay, so I'm going to tell you it's beta decay. So I could put this, and then I have to make 79 the number on the bottom on both sides. So I had to put an 80 there, and then 211. And then, hey, what do I put here? We'll check a PT and find 80, and you will find Hg, mercury. Okay, so this is a nuclear reaction, a spontaneous beta decay. Hey, Homer. All right, so here's the third type of radiation that we're going to talk about, gamma radiation. Yes, that's what made the Incredible Hulk. It is like a Greek letter G. It's a 0, 0, looks like a check mark kind of. It's a gamma ray. It has no mass and no charge. It's just high-speed energy. No mass, no charge. But because of that, because it's high-speed energy, it has most penetrating power. It's shielded by lots of concrete I know you can't see that very well, but you heard me say it. Shielded by lots of concrete, and even then, not so good. Okay, so this element is radon 230. It's the isotope of radon, and it undergoes beta decay and gamma decay. So you write the symbol for radon. We know the mass number is 230 because the dash is to the mass number. And we look up radon in the periodic table, and we find it, element number 86. Undergoes beta and gamma decay. So it's going to decay. So I got an arrow, and beta is 0, -1. E, which we learned on the last slide, and then gamma is 0, 0, this, gamma. So wait a second. In order to finish this reaction, we need to show the total. So this is 86 on this side, this is -1 on that side. So we need an 87 so that these together equal 86. And we need to do 230 on top. I know I'm writing on the Incredible Hulk here. Element number 87 is... if I could find it on the periodic table, francium. Okay, so make sure that these bottom numbers on both sides of the arrow equal each other on the top. We'll save this one for class, okay? So get ready to do it. Try it on your own, and then maybe I'll ask about it on the open note quiz. So we talked about this band of these dots are stable isotopes. So they don't do anything. They just live happily ever after. Okay, but if there's a dot above it or below it or up here, then it's going to give off radiation, and because it's unstable. So let's see, if we had 10 protons and 15 neutrons. So here's atomic number, that's protons, 15 neutrons. It's right about there. It looks like it's on the band of stability. So this is stable, and it will not be radioactive, okay, because it's on the band of stability. What if we had an isotope with 40 protons and 20 neutrons? So here's 40 protons up and over what? This is not on the band of stability. So what does that mean? It means it's unstable. What do unstable nuclei do? Give off radiation. Right? What about 70 protons and 112 neutrons? So 70 protons and 112 neutrons. 70, whoa, come on, get up there, 70 protons and 112 neutrons. It looks like we're on the band, so it's stable and will not give off radiation. No radiation. Okay. What if it's bigger than 83 protons? So here's 83 protons, we're up here. Guess what? No dots up there, so unstable. Okay. Gives off radiation. Now, if atoms are really heavy, the kind of radiation they're going to give off is probably alpha particles, because every time it gives off a 4,2 He, then the nucleus gets lighter by 4 particles. Okay, so heavy, unstable isotopes usually give off alpha radiation. Okay, so how do we explain that there's these stable atoms? Why are any atoms stable? Well, there's a force between subatomic particles called the strong nuclear force. And what the strong nuclear force is an attraction of protons to protons, neutrons to neutrons, and neutrons to protons. Now you might be saying, hey, but protons are positive and other protons are positive. Why would they even stay close? Wouldn't they repel each other? Well, there's some neutrons in a nucleus too, and those neutrons kind of act like glue to allow the protons to stay together in that nucleus. And it's like, I like to call it mini gravity. I know a physicist would probably just say, you can't do that, Harbin. But I think of the strong force as this attraction that's like little mini gravity in the nucleus that keeps all of this stuff together. And the neutrons are kind of like glue in that strong force. Okay, this is a little bit different. All of this radiation, that's what this is, radiation, is electromagnetic radiation. Okay, so this is light waves, high energy, lower energy. Here's what we see, visible light. Okay, and so well, I said light waves, but this is all electromagnetic radiation. It's not particles. The higher the energy, the more chance they have to ionize things, which means knock electrons off stuff to cause ions to form. And look, here's where gamma radiation is. It's pretty high energy. It is ionizing. Alright, just to review, we need some music, okay? Alpha, 4,2 It's a positive 2 charge, heavy, mass of 4, and pretty big. So you can block them with paper, okay? Beta, 0, -1, Right, negative charge. They can get through a little more because they're a little lighter with more energy. Positron, I didn't say it in the video, but, well, I'm saying it now. It's just like a beta particle, except it's a positive instead of a negative. Right? Gamma is massless, and it has the highest penetrating ability, so it takes the most to shield it. Right? If it's on the band, it's stable. If it's off, it's unstable, so it's going to give off radiation. These are the radioactive ones. Right. And then 83 is the biggest unstable element. Alright? Hey, read chapter 25. Alright? You can get your automatic 10 if you want to do it. Alright? It's the second time I tape this because I care. I want you to learn. Alright? Peace out. After you look at these objectives again. Only 5 things to learn. We'll keep going. I'll see ya. Shout out. Hey, how about this is period 1's final shout out. Alright? And then period 2, you'll get the last one. Peace out.